Hello, people of the world, students, teachers, tea drinkers. My name is Addison Allen. I'm Addie Al, the science gal, because gal and my last name is Allen Al. So it rhymes, but one of my friends came up with that. Anywho, I'm here today to talk to you in this little education station about light and optics. And I'm only going to be doing the first part though, because someone else has the second part. That's coming up later. Okay, so yeah, I'll be doing that. I'll be filming it over the next couple of days. So that'll be a thing, because if I tried to do it on one day, it wouldn't get done. Simple as that. And I'll be using filters because I can, and it's fun, and like light and stuff. So it works. It's incorporated. So there you go. Okay, here we go. So first off, in this little bit, we're going to talk about frequency. So frequency is basically how often an event occurs within a certain amount of time. But in physics, it's usually talking about a certain amount of oscillations in a second. So I've got this little diagram here, and I mean, it's upside down. It's an easier way to just visualize, basically. So you've got one oscillation right here, and then there's another. It's a cycle, it's repeating. Basically, we're trying to see how many times this can repeat in a certain amount of time. And that is what frequency is, basically. Next up, we've got wavelength. So basically what wavelength is the length between two crests or two troughs on a wave, but it's usually going to be the crest. That's just easier to look at. So we're bringing back the diagram. It's right side up this time. This is one peak of a wave. This is another. And this distance right here is a wavelength. It's about as simple as it gets. Need to do a filter. So the electromagnetic spectrum is the ranges of all electromagnetic energies and waves. And this isn't mechanical. It's just electromagnetic. Two completely different things. Nearly all objects on the Earth emit some type of light, or transmit it. Whatever works for them. And the distribution of this light along the electromagnetic spectrum is determined by the object's composition. There's actually a branch of physics that studies this. It's called spectroscopy. Yeah, that's a thing. So you got all kinds of energies and waves being emitted by electromagnetic radiation with the electromagnetic spectrum, and I'm going to talk about all of them from the lowest energy in the longest wavelength to the shortest wavelength and the highest energy. So here we go. Also, forgot to mention, there are two different sides to this electromagnetic spectrum, and that is low EM waves and high EM waves. And of course, EM stands for electromagnetic. And so low EM waves are from radio waves up to visible light. And then high EM waves are from visible light to gamma rays. So the differences in frequencies and wavelengths, and they're separated by the visible light spectrum. First up, longest wavelength, lowest energy, is radio waves. A radio wave is an electromagnetic wave with a range of radio frequencies. You've got a radio signal, which is just a wave. But then you've got AM and FM. So what AM is basically what you see on an Arctic Monkeys cover. That's what an AM is. And then FM is basically a longitudinal sound wave. So it compresses, expands, and all that good stuff. And certain frequencies for radios are picked up by different sized antennas. Antennas on cars and phones and radios. So yeah, that's how it works. Those are what they're designed for. Next up, we've got microwaves. And microwaves are obviously used in microwave ovens to cook. But they're also used for transmitting information and radar equipment. Okay, so for this part, I went downstairs and I got two different mugs with two different drinks, and my mom was like, "Why?" It's for science! Anyway, so basically what we're dealing with now is infrared rays. So, waves? Rays.
So infrared waves show us basically how much heat something has, like using... So infrared waves basically tell us how much heat an object has and what heat it's giving off. It's usually used in thermal imaging, if you catch my drift. My phone vibrated again. I'm not going to cut that out. Sorry, not sorry. So thermal imaging would look a little something like this, although this camera doesn't use actual like infrared like rays, so it's not exactly accurate, but it's as close as we can get. And what's going to happen here is cold objects aren't actually cold. Cold's not really a thing. It's like something humans made up. Cold objects are just less hot than other hotter objects, and infrared images show, you know, heat in different colors, and they're used to represent different temperatures. So I've got these two different drinks that I was talking about earlier. And this one has got ice water in it, and so it's kind of dark up in here. That's where the ice is. That's where the cold stuff is. And then we've got this tea. It's just tea. And you can see they're different colors. This one's brighter than the other because they're different temperatures. That's how infrared works. And infrared can travel through different mediums, or at least through different thicknesses of barriers. So it can go through thick smoke or dust or fog, stuff like that. So firefighters use infrared imaging to find people in houses or buildings that are on fire. If you see. So up next on the electromagnetic spectrum, we've got visible light, which is, the stuff that we can actually see. That's why it's visible light. Human eyes can see it, you understand? Wavelength of different, lights determine the color and what we see, and that's all the colors in the rainbow and whatnot. You've got the mnemonic Roy G. Biv, which is red, orange, yellow, green, blue, indigo, and purple. Most of the light that we'll actually interact with is some form of white light, which contains most or all of these different wavelength ranges. Shining white light through a prism causes the wavelengths to bend at different angles, refraction, you feel me? And so the result is the different colors split. That's the visible spectrum, the visible light spectrum. That's why we can see all the colors of the rainbow in a prism. So refraction is what makes us be able to see the rainbow in the sky, but instead of, a medium like a prism, it's actually airborne water particles acting as a refractive medium. So the sun emits different wavelengths in the electromagnetic spectrum, but it's actually ultraviolet rays that cause our sunburns. We can actually use UV light to study stars and galaxies and all of the wavelengths that they give off, which is how we get pictures of them. You understand? So we're looking at the gas around them and their atmospheres and whatnot, and we use visible light to see the different wavelengths of ultraviolet, because there's actually a couple of different ones inside of that, but I'm not going to get too deep into that. So comparing, with data and that kind of stuff, astronomers can actually learn different things about the structure and evolution of galaxies, and that's all thanks to ultraviolet light and stuff that they can capture. So there we go. It can sometimes be good, but you don't want to get too much of it from the sun, or sunscreen. So guess what we're going to talk about next? X-rays have smaller wavelengths and therefore a higher energy than ultraviolet rays. X-rays actually see shadows left by things that X-rays can't travel through. So things like bones and teeth that are actually really dense absorb more X-rays than your skin does. So you see the silhouettes of your bones and your teeth left on an X-ray film, while your skin appears transparent. But like ultraviolet light, you don't want to hang out too much around X-rays, because too much X-ray radiation can get you sick and can give you cancer. So, hang out around that too much and it's not good. So last but not least, on the electromagnetic spectrum, we've got gamma rays. Gamma rays have the shortest wavelength and the highest energy of any wave in the electromagnetic spectrum. These waves are usually generated in radioactive atoms and in nuclear explosions. Gamma rays can actually kill living cells, which is why we use it in medicine to fight cancer. You know, you concentrate gamma rays on a cancerous spot and it'll kill the cancer cells. So, last we're going to talk about the speed of light. And so, light travels really, 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 really fast. It's like 3 times 10 to the 8th meters per second, or something like that. Or 186,000 miles in a second, which is still really fast. But light travels slower through different mediums, like air or water and stuff like that, which is why some things look opaque, translucent, or even just invisible. It happens. And that's the end of that. So, thanks for watching.